Okay. Radiation resistance of a small dipole current element of length L at a frequency of 3 GHz is 3 ohms. If the length is changed by 1%, then the percentage change in the radiation resistance rounded off 2 decimal places is dash. Okay. So here they have given the radiation resistance of a small dipole current element of length L at a frequency of 3 GHz is, so at a frequency F is equal to 3 GHz. So they have given the radiation resistance is equal to 3 ohms. So at a frequency 3 GHz, the radiation resistance is equal to 3 ohms. Now if the length is changed by, if the length is changed by 1%, if the length is changed by, so length is changed by 1%, length is changed by 1%, okay, 1%, then the percentage change in the radiation resistance rounded off to 2 decimal places is, okay. So length is changed by 1% means how we can represent the change in length here, how we can represent the change in length, that is nothing but I can write it as what, dl by L into 100%. They have given us what, they have given us 1%, they have given this as 1%, understood, okay. So this they have. Now so whenever the length is changed by 1%, then what is the change in radiation resistance? So you have to determine the percentage change in the radiation resistance. So that is change in radiation resistance with respect to radiation resistance into 100%. So this is what you have to determine. Okay. So now they have given at the frequency F is equal to 3 GHz, radiation resistance is equal to 3 ohms. See, we know that due to a small dipole, the radiation resistance is given by 80 pi square into L by lambda whole square. So this is the expression for radiation resistance. Okay. So now here you want to determine what? You want to determine the percentage change in radiation resistance. So here what I am going to do here is I am going to differentiate on both sides. With respect to length. Okay, so if I differentiate on both sides with respect to length, what I am going to get here? Here I am going to get 80 into pi square into 1 by lambda square into 2 into L. Okay, so this is what you are going to get. So here this one I can write it as what? This one I can write it as 8 into pi square into L by lambda whole square multiplied by, I can write it as 2 into L. Okay, sorry, 2 divided by L. So I can write it as 2 divided by L. So here I have multiplied with here I have multiplied with L and divided with L. So I am going to get what? L square here. So I can write this as L by lambda whole square multiplied by 2 divided by. Okay. So now if you observe this 80 pi square into L by lambda whole square is nothing but what? Is nothing but radiation resistance. So therefore so D radiation by DL is equal to what? Is equal to, I can write it as R radiation into what? Into 2 by L. So therefore I can write this as, so the change in radiation resistance is equal to, I can write it as 2 into DL by L. Okay, so if I multiply the so this is the change in radiation resistance. So if you want in terms of percentage, so I can write this as what? DL by L into 100%. But what is the change in length here? So DL by L into 100%. What is the change in length they have given? Is nothing but 1%. So replace this with 1%. So here you are going to get 1%. So this is multiplied by 2. So therefore the change in radiation resistance, whenever there is a 1% change in length is nothing but 2%. So whenever the length is changed by 1%, the radiation resistance is going to change by what? Change by 2%. Okay. In the table shown, list 1 and list 2 respectively contain terms appearing on the left hand side and the right hand side of Maxwell's equations in their standard form. Match the left hand side with the corresponding right hand side. Okay. So now they have given list 1 and list 2. They have given list 1 and list 2. So we know that these are the Maxwell's equations. We know that these are the Maxwell's equations. So these are the Maxwell's equations. So first Maxwell's equation, divergence of D equal to rho V, divergence of B bar is equal to 0, divergence of E bar is equal to minus dou B bar by dou T, and del cross H bar is equal to JC bar plus dou D bar by dou T. Okay, so these are the Maxwell's equations. So from this Maxwell's equations, we are going to match the list 1 with list 2. Okay, so first one they have given as divergence of D bar. Divergence of D bar is equal to rho V. So first one will match us to what? Will match us to Q. First one will match us to Q. Next second equation they have given us del cross E. Del cross E is equal to what? Minus dou B by dou T. Del cross E equal to minus dou B by dou T. So it will match to what? It will match R. It will match to R. And third Maxwell's equation, third one they have given as divergence of B bar. Divergence of B bar is equal to 0. Divergence of B bar is equal to 0. So it will match to P. So third one will match to P. Next fourth one, del cross H. Del cross H is equal to what? J plus dou D by dou T. So fourth one will match to S. Fourth one will match to S. Okay. So which one is the correct option here? For first one Q, second one R, third one P, fourth one S, and hence option A is correct. And hence option A is correct. Okay, so this is the correct answer. Next question, what is the electric flux through a quarter cylinder of height h as shown in figure due to an infinitely long line charge along the axis of the cylinder with a charge density of Q. Okay, so here we know that if you consider a infinite line charge, okay, so the flux leaving through this cylinder due to an infinite line charge. Okay, we already know that the total flux that is leaving through the cylinder, the total flux that is leaving through the curved surface of the cylinder. We know that there will be no flux through top surface and there will be no flux through bottom surface due to an infinite line charge. The flux will be only through the curved surface of the cylinder. Yes or no? So the height of the cylinder, let us consider the height of the cylinder is h. The height of the cylinder is h, and the charge density they have given as what here? The charge density they have given as Q. So charge density they have given as Q. Charge density is equal to Q they have given. Okay, so now they are asking to determine the flux through what here? Quarter part of the cylinder. See, we know that the total flux that is leaving through this curved surface, is equal to what? Is equal to the total charge enclosed by this surface, the total charge enclosed by this closed surface. What is the total charge it is enclosing here? The charge density is Q coulomb per meter, and its height is what? Its height is h. So it is going to enclose the total charge, that is nothing but what? Q into h divided by what? Divided by epsilon naught. So this is the total flux leaving through the surface of the cylinder, Now they are asking to determine the flux through the quarter part of the cylinder. So let us say this is the quarter part of the cylinder. So through this region, so we have to determine the flux through this quarter part of the cylinder, Okay, so through this quarter part of the cylinder, you have to determine the flux. Through this quarter part of the cylinder. Okay, so this region you have to determine. Understood? Okay, so how to determine here? So this is the total flux through the through the total curved surface of the cylinder. So now the flux through quarter part of the cylinder. So the flux through quarter part of the cylinder is nothing but what? So this is the total flux. You want only the flux through quarter part. So that means that is quarter part of this flux. That is nothing but you have to divide this what? You have to divide this with 4. Okay. So quarter part of the cylinder, that is double integral E bar dot dA bar is equal to, this represents the flux through quarter part of the cylinder. So this is equal to total flux divided by what? Total flux divided by 4. So this is equal to what? This is equal to QH by 4 epsilon naught. So this is the total, this is the flux leaving through quarter part of the cylinder. And what is the answer here? QH by 4 epsilon naught. So that is nothing but option B. Option B, QH by 4 epsilon naught. So option B is the correct answer. Okay. So this is the end of this question. A rectangular waveguide of width W and height h has cutoff frequencies for TE10 and TE11 modes in the ratio 1:2. The aspect ratio W by h rounded off to 2 decimal places is. Okay. So they have given the cutoff frequencies. They have given the cutoff frequencies for TE10 mode and TE11 mode. Okay. So that is, they have given the ratio of cutoff frequencies of TE10. So TE10 mode, the cutoff frequency I am writing as FC10, and for TE11 mode, the cutoff frequency I am writing as FC11. So this ratio they have given as what here? They have given as 1/2. This ratio they have given as 1/2, and they are asking to determine what? To determine W by H ratio. W by H ratio. So this is the rectangular waveguide. So this is the rectangular waveguide. So W represents what? W represents the broader dimension, and H represents the shorter dimension. So W by H ratio is called as aspect ratio. Okay, you have to determine the W by H ratio. See, we know the formula for FC10. So for FC10 I am writing simply FC10. Now I can represent this FC11. I can represent this FC11 in terms of what here? FC10. How I can represent here? So we know that FCMN, the cutoff frequency, FCMN is equal to C by 2 into square root of M by A whole square plus N by B whole square. N by B whole square. So this expression I can write it as C by 2A into square root of M square plus A by B into N whole square. A by B into N whole square. So this is C by 2A. This is C by 2A is nothing but FC10. So this is the cutoff frequency. C by 2A is the cutoff frequency for what here? FC10. So FC10 into square root of M square plus A by B N whole square. So here instead of A they have given as W, instead of B they have given as what? They have given H. So if you want, you can replace this A with W and B with H. Okay. So A represents broader dimension. Okay. And B represents shorter dimension. So instead of A and B, you can use here W by H. Okay. So W by H into N whole square. So this is how you can represent. So the cutoff frequency, any cutoff frequency you can represent as what? So here this is C by 2W. Okay. So any cutoff frequency you can represent in terms of what? In terms of FC10. That is in terms of dominant mode. So now here they have given FC11. So this value is M value is 1, N value is also 1. So substitute here M equal to 1 and N equal to 1. So what you are going to get? So FC11 I can write it as FC10 into square root of 1 square plus W by H. W by H, N value is also 1. So whole square is equal to what? This is equal to 1/2. FC10 will get cancelled. So we are going to get here 1 by W by H whole square. So if you do the mathematical, if you arrange these terms in this manner, you are going to get 1 plus W by H whole square is equal to 4. Therefore W by H is equal to what? W by H is equal to, you are going to get √3. You are going to get √3. So therefore W by H ratio is equal to what? √3/1. root 3 by 1. Okay, so root 3 by 1. So this is the answer. W by H ratio is equal to root 3 by 1. You know the root 3 value, that is 1.73. Understood? So this is equal to 1.73 something. Okay, so this is the end of this question. Next question. Two identical copper wires W1 and W2 placed in parallel as shown in the figure carry currents I and 2I respectively in opposite directions. If the two wires are separated by a distance of 4r, then the magnitude of magnetic field B bar between the wires at a distance r from W1 is. Okay, so this is the question they have given. Now see here, so they have given two identical copper wires W1 and W2 are placed like this. So here this is W1 and here another wire W2 is present like this, and here at a distance of, the distance from here to here is r, and the distance from here to here, is how much here? The overall distance is 4r. The overall distance is 4r. Okay, so that means the distance from W1 is r and the distance from W2 will become what? Will become 3r. So they are saying that these two current carrying wires are carrying the currents I and 2I respectively in opposite directions. So W1, let us consider W1 is carrying a current I. Let us say W1 is carrying a current I, and W2 is carrying a current 2I in opposite direction. So that means it is going, the current will be in this direction. Understood? So now you have to determine the B field. At a distance of r from W1. So you have to determine the total magnetic field or net magnetic field at a distance of r from W1. So now if you observe this current is flowing in this direction. So due to this current, the B field at this location, is going to point into the board. So due to this current carrying wire, the B field is going to be produced into the board. So here this B field, I am calling it as what? I am calling it as B1. So this is the B field that is produced into the board at this location. So this is due to W1, and W2 is carrying the current in this direction. So due to this current, the B field at this location is going to point into the board. So due to this 2I also, the B field will point into the board. So here due to this current, so B2, so wire W2 is going to produce the B field. So it also going to point into the board direction. Now if you observe B1 and B2 both are pointing in the same direction, so the net B field is going to get added up, So therefore the net magnetic field at a distance r from W1, is equal to B net is equal to what? Is equal to B1 plus B2. So we know the expression for the B field. Produced by a current carrying wire of infinite length. Yes or no? So what is that expression here? B1 is equal to what? B1 is equal to mu into I divided by 2 pi into normal distance from the wire. What is the normal distance from the wire here? Is nothing but r. Plus what is the expression for B2? So B2 is mu into, what is the current it is carrying? W2 is carrying 2I. So mu into 2I divided by 2 pi into normal distance from W2. What is the normal distance from W2? Is nothing but what? 3r. So now here I can take mu I by 2 pi r common. So then I am going to get here 1 plus 1 plus 2 by 3. So I am going to get 1 plus 2 by 3. So if you do this, you are going to get what? 5 mu I by 6 pi r. You are going to get 5 mu I by 6 pi r. Understood? Okay. So the option, so hence the option A is correct. So for this question, option A is correct. So this is the end of this question. So next question, the dispersion equation of a waveguide which relates the wave number k to the frequency omega is k of omega is equal to 1 by c into root over omega square minus omega naught square, where the speed of light c is equal to 3 into 10 power 8 meters per second and omega naught is a constant. If the group velocity is 2 into 10 power 8 meters per second, then the phase velocity is, okay. So for this question, we know the relation here. We know the relation between phase velocity, group velocity and velocity of light. So that is nothing but from rectangular waveguides, we know this relation. The phase velocity into group velocity is always equal to what? Is always equal to c square. Okay. So therefore the phase velocity is equal to c square by what? C square by group velocity. So here c is nothing but what? 3 into 10 to the power of 8 whole square. So they have given the group velocity. They have given the group velocity as 2 into 10 to the power of 8. 2 into 10 to the power of 8. So you are going to get 9 into 10 power 16 divided by 2 into 10 power 8. 2 into 10 power 8. So if you do this, you are going to get what? 4.5 into 10 to the power of 8 meters per second. 4.5 into 10 to the power of 8 meters per second. Okay, and hence option D is correct. And hence option D is correct. Okay, so this is the end of this question.